My faith in Starbucks has been restored. I came in late last night. I couldn't find a Starbucks anywhere. I'm in Seattle. This is where Starbucks is. This morning there was like 20 of them in every corner. So I think I was just really tired. But triple espresso. So this should be a fast talk. Anyways, I'm JT. I'm from Embarcadero Technologies. We're based primarily in Scotts Valley, California. Does anybody know where that is? One person.
Is that what Borland is from?
That's where Borland is from. Exactly. Yeah, there's a history there. I'll get into that in a moment. But it's right above Santa Cruz, which is in the Monterey Bay. And so I was surfing this weekend in very large waves. I wasn't sure if I'd be making it to this conference. It was a little scary. And then we're just, probably about 60 minutes from San Francisco. So Silicon Valley without Silicon Valley. It's kind of a nice spot. And what I'm going to share with you guys today is some thoughts on user interface development, rapid prototyping using C++. How many of you out there are building user interfaces with C++ today? And you know what's interesting to me, looking at some of these other sessions, that this is pretty representative, I think, of the C++ community at large. The percentage of people who have to write user interfaces in C++, it's actually pretty small compared to the larger C++ community. Yes, of course, C++ can do all sorts of amazing things. It can also do UI very well. And so I'm going to talk about methods to do user interface development, prototyping. It's largely tooling, but there needs to be some language support and framework support to make that happen as well. So we'll get into some of those details as well. This becomes particularly challenging when we're talking about devices, not just desktops. In the old days, 10 years ago, we'd be building software right on our Windows desktop and deploying it right to our Windows desktop. And so you could get that feedback pretty quickly in this development cycle. Today, if you're targeting mobile devices, like iOS or Android devices or others, that cycle takes a lot longer because you have to package and deploy and install and go through all these machinations just to get your app up and running remotely. And then, of course, attaching debuggers, et cetera. This can be a long process. And when you're doing that 100 times a day, those seconds add up. So that's kind of what we're going to talk about today. A little bit about myself. I've been developing for a long time. Probably like many of you, started way back in the 80s. I was a VIC-20 guy, though. I didn't do the TRS-80. I went the Commodore route. And Amiga, for that matter, for a little while. Mostly basic, some C. Then I went to school at UCSC. That's in Santa Cruz. That's how I got to Santa Cruz. That's where I did my C++ work. And I, at that time, thought I was going to be a game developer writing game engines, which was cracking me up because I saw Euler as the name of the room, and I started thinking about camera problems back in the day, and gimbal lock with Euler angles and quaternion space, and got me all excited again. I was looking for some of that code last night to play with again. But I ended up actually finding out that Borland was local to that area, and they were the C++ compiler that I had been using, actually borrowed from a friend back in the day when I was on DOS. And so I ended up getting an internship there early on, and was in the C++ team that built C++ Builder, which was a rapid prototyping solution with C++. After that, after Borland kind of got out of the tool space, it seemed for most, I went into the Valley and did a bunch of work in mobile and embedded companies, mostly in embedded Linux, which kept C and C++ very alive in my mind. I sort of missed all the Java movement, thankfully. And a little time of research in Motion, too, helping them move to C++ before they couldn't sell devices anymore. And then came to Embarcadero about 3 years ago. Embarcadero, as someone noted, is in the same place as Borland. And actually what's going on there is Borland bought the tools, or Embarcadero bought those tools from Borland. So Embarcadero is basically the old Borland crew. And we're all a little older, a little bigger, but we're still building tools and having a great time. And what we're doing in particular is we're building tools for C++ developers to build apps not just for Windows, which was our heritage, but also for Mac OS X, iOS, Android, and beyond. So that's the stuff that I'm involved in today. So let's start with the definition. What is a device? So at its most basic level, a device is something that can run programs. It needs a CPU, it needs some memory, it needs some I/O, and at a very minimum, it needs some type of RTOS that you can write a program into. That I would classify as an embedded device, typically headless, a lot like you see in these Internet of Things gadgets these days where they're capturing a heart rate or something like that. Very tiny device, little microprocessor, 8-bit probably, running in, like we used to write programs in 64K back in the day. Now, if you get to the next stage where you add a display and some type of input, touchscreen input in particular, you're talking about mobile devices. And that's what most people think about when they think about a device. But what's really interesting about what's gone on in the last 5 years or so is that much of these devices are really app-ready operating systems now. You know, I was just thinking about this the other day. When I was at Borland, we worked on a mobile development environment for Symbian. Does anybody remember Symbian? And they actually were ready to, they had this all ready to go. You could deploy apps to this thing. I mean, the one thing they missed was the App Store. That was the big difference. That's what I think Steve Jobs recognized and really created something big out of it. But in any case, the main operating systems that are app ready, of course, Windows is the original app platform, but iOS and Android as well. The ability to package applications, distribute them through some type of mechanism that people can access on that device, install the package, run the application. So that's kind of what we're really targeting is devices that are app ready, and you can build C++ applications for them. They can be distributed and deployed through the standard distribution mechanism, typically an app store. Although Android is way easier, you can just grab an APK, throw it anywhere you want, download it, and off you go. We'll talk about that a little later when it comes to rapid prototyping. Out of interest, how many of you are doing mobile development today? Some of you, okay. Out of that, how many of you are targeting iOS? And how many are targeting Android? Okay. So this, what I'm seeing a lot is most people are targeting both. Because if you're doing mobile, it's hard to make a choice. You really have to target both to be successful. It depends on your business model, it depends on your customer. There's something to be said for iOS in the sense that people make more money on it. But then there's something to be said for Android when it's 85% of the market, especially outside of North America. So interesting times. And then today, of course, in about an hour, Apple's going to introduce the next revolutionary device. And we all think it's a watch, right? So this will be interesting. People will start wearing watches again. But it's really, what I think is interesting, it's all about the client. Again, back in the 80s, that's kind of all you had. Well, I mean, you had mainframes. But if you were a programmer or you were building apps, it was kind of for yourself or for your business, and it was all about just the client. Didn't really do much with the back end or mainframe much. And then it started getting into this back end business where a lot of the apps are written on the back end and generally displayed via web browsers. That was much of the late 90s and early 2000s. But around 2005, it all changed back to the client. So I think we'll see these cycles go on and on. These days, it's kind of a combination. You really should distribute your apps across many tiers, especially with the Internet of Things. But the client is where most people spend their time. How many of you have any teenage kids? A few of you? Okay, I have a 15-year-old daughter. She invites her friends over. They sit on the couch, and they all look at their phones. They're actually having conversations, but it's on their phone to one another. Yeah, some adults as well, sure. Their lives are very social, but it's kind of inside the device. They're like attached to this 4-inch device. It was bizarre. You're sitting next to somebody, just talk to them. You don't have to send them a Snapchat. Anyhow, I feel like I'm getting old now because I don't get the younger kids. But what's interesting about it, it's all about the client again. Right now, it's all about that 4-inch device more than anything, especially for the bulk of the consumers out there. I love this chart because it goes back all the way to when I first got into computing. And up until about 1985, you had a lot of choices if you wanted to play with the client operating system. And like I said, I went the Commodore/Amiga route. You had other choices. Atari even had a system. Amiga, Trash 80s were kind of still fairly popular then. PCs were just coming out. ARM had a system, that's right. Yep. And so what's interesting about this, though, is that you still had a lot of choice. The Intel or Wintel monopoly or duopoly hadn't quite kicked off yet. But that was about the time, 1985. All of a sudden, all you targeted was Windows. That's all you wrote applications for. You bought Petzold's book. You labored through Windows API, and you wrote Windows programs. And that went on for most of my career, up until about 5 years ago with the revolution around the iPhone and around Android devices. And today, what we're looking at is a situation where Windows as a client operating system represents less than 50% of usage now. So that's pretty amazing that this all happened in the last 5 years. That doesn't mean Windows isn't important. It absolutely is, especially for most enterprises and businesses. But it also means that if you're targeting application development, mobile is critical. And of course, that's largely made up of Android and Apple today. The other thing I think is interesting is how devices are used. You know, I was talking about the 4-inch device. That's where most people spend their time looking at their phones. But actually, we use many devices throughout the day. I personally prefer a laptop. Of course, it gets hot when it's sitting on your lap. But this kind of, I think, mirrors my usage as well. In the morning, you wake up, I don't know, this is me. I check my messages because we're a worldwide organization. A bunch of emails come in through the night from Europe or Asia or whatever, and you know, I start dealing with it on my mobile device. Get to work, mostly use my laptop throughout the day, dock to a 4K monitor. I was just talking about that because I get 800 by 600 on this. It's like that many pixels on my 4K monitor. So it's mostly using a real production workstation throughout the day. You get home, generally you're going to be using a tablet because you're playing games or looking at the internet. Now, maybe I'm different, but I think most people probably have a bunch of these different types of devices and do largely use them throughout the day like this. Yeah, on the train, exactly. On the way home, commute home. Sit on your tablet, connect to Wi-Fi, or play solitaire, whatever it is that you're doing on the tablet. The thing is that now you're not just dealing with multiple operating systems, but you're also dealing with multiple form factors. So there's a big difference between writing an app that lives on a 4-inch device in portrait mode versus a tablet that's in landscape and gives you all this extra real estate versus a workstation. So as an app developer, this is challenging. And especially if you're trying to prototype applications to give your customer input on how this is going to look on multiple devices, that's going to be the biggest challenge. I actually kind of missed a discussion of why prototype and what's the importance of prototyping, and I think maybe this is a good segue into that. But prototyping is, you know, probably in the old days we would sit there on a whiteboard and write a couple boxes and say, this is kind of the layout that we want to look at, and then we'd go try to build it. And generally, what you built didn't look anything like or remotely like what you put on the whiteboard. True of paper design or paper napkin design. This is a big challenge for companies or programmers who also get fed UIs from designers, who spend their time coming up with these amazing designs in a graphics package and expect you to just magically create that. And this is a very tough cycle. What you end up with, unfortunately, is a lot of unmet expectations and disappointment. And so if you spend a lot of time building a UI, delivering it, and not meeting the customer's requirements, that means you have to go back and redo a lot of work. So prototyping or rapid prototyping is useful because what you try to do is build out pieces quicker and get feedback more often and make incremental steps towards building. This is, you know, I'm sure everybody here is familiar with agile methodologies versus waterfall. This is a lot like the agile version of UI development. And the critical thing here is get feedback. And you need a mechanism to be able to provide that delivery of that UI so that you can get that feedback. If you can do that, you're well on your way to rapid prototyping. And it's going to save you a lot of pain. How many of you have been through that cycle where 6 months down the line you deliver a polished product with the UI that didn't meet the user's expectations and you spend a lot of time reworking the UI? Yeah, I should see pretty much every hand up, especially if you're doing app development. So that's where I think rapid prototyping is going to help. Here's the next challenge. This diversity is just going to get even crazier. Like I say, in about 45 minutes, Apple's going to introduce the watch, and now people are going to start wearing jewelry again, and we're going to have to wear a bunch of wearables with all these inputs and biometric devices. And how many of you ever read the book Snow Crash by Neil Stephenson? We're all going to become gargoyles. You remember that character? The guy who was wearing all the electronics and capturing everything going on around him? So this is kind of where we're headed to for a little while. I think another cycle, people are going to overdo it again for a while, and then we'll figure out how to make it fit into our lives in a reasonable way. So this is something that we have to look out for. How do we build apps that can leverage all this goodness and technology, but do it in a way that, keeps us using it in a productive way, not having technology rule our lives. Like my daughter sitting there on her phone with her friends, technology is ruling her life. It's not the other way around. And that's what she's going to learn, maybe. Maybe she'll just become a cyborg. So 5 years later, after iPhone, apps are everywhere. That's what people want to talk about. That's what people want to deliver. That's how people think about application development. Of course, we know there's a lot more that goes into app development. There's a lot of back-end work. Maybe you have an enterprise with a bunch of databases and you're doing a lot of your logic on the back end. But at some point, you're going to have to deliver an app to a mobile device or to a desktop because that's where your end user is going to interact with it. They're not going to log in through a terminal onto your Unix system and interact with the app that way. Those days are long gone. They're going to say, where's my iOS app? Because I want to use it on my iPhone. The good news is C++ is everywhere too. So there's no reason why C++ isn't a viable language to do this. There are challenges there, don't get me wrong, but I think we can talk about how we can solve some of those in this next 40 minutes or so. I think C++ is perfect for these types of apps, personally. First of all, it was designed basically as a cross-platform language. It was meant to be close to the hardware, but also be removed enough to be used on multiple operating systems. As such, you'll find a C++ compiler on every single operating system out there. So it's available, and you just need to know where to look for it or how to interact with the system that you're working with. It's also, it was really designed for small applications, for embedded devices. I mean, it's perfectly suited for this type of development. So why hasn't it taken over the world? I mean, it is enjoying a bit of a resurgence, I would argue, especially with C++ 11 and 14 now. But why hasn't it taken over the world? I think, part of the reason is that there was a change in architecture in the late 90s and in early 2000s. We were talking about people were writing back-end code. That was the way to build apps. They were using Java and .NET primarily to do this. And it was scalable. You could scale because you could just throw in another blade into your back-end system and scale your bandwidth that way and your CPU bandwidth. But people were delivering basically web user experiences this way, largely browser-driven applications. You could certainly connect to it with rich client apps, and people did, but most people were used to this browser experience. This defined, I think, much of the early 2000s. With client devices, like we're talking about, the user experience expectation is different. If you're using a browser, you're okay with the fact that when you click on a link, there's going to be a lag, right? There's going to be latency with regard to some kind of request going out over the internet and some type of page being delivered back to you and having to paint inside the browser. If you're on an iPhone or an Android device, there's no way you're going to put up with that unless you're in a browser. You see browser Chrome, I'm okay with that. You see an app, I'm not okay with that. Apple really, I think, one thing that they did well was they really made that interactive user experience really visceral. I mean, as soon as your finger touches that scroll button, it's almost like it reads your mind. And that's kind of like the latency expectation that end users have now with regard to client applications. Here's the challenge, though. You have a fixed hardware profile. You can't scale like you used to with these virtual code-based solutions. So you have to write smart apps. You have to use languages, or generally try to use languages that can deliver on this type of performance. So your user experience is bound by the hardware profile that's on the device largely. And therefore, again, delivering that user experience with the high performance that's expected, we're starting to see this growth again of native application development. So Objective-C, of course, that's the native code language. Maybe I'll take an aside here. The term native has been grossly misrepresented over the last few years too. It used to mean, at least to me, compiled code. And a lot of companies have co-opted the term to mean, oh, I could package it and put it through your app store, therefore it's native. And unfortunately, that's what it turned into. That's what most end users expect now. If I can download it from an app store, install it, have an icon that I can click on my tray there, then it's a native app. But that's really not native. When we talk about native, of course, we mean basically non-web technologies. So you can certainly write apps with web technologies for these devices using HTML5, JavaScript. There's actually lots of ways to write apps, but they're not native. Objective-C is, C++ is obviously, Java isn't, but what people like, or companies like Google are trying to do is trying to compile that as well. So they're trying to get the best of both worlds in there, which there's going to be challenges with memory management, garbage collection, and all that other stuff that marks a big difference between native and virtual code. So I was trying to think of that, why isn't C++ used on all these devices? I think it's still true that a lot of developers, especially those who got into development in the last 10 years or so, think C++ is really complicated. I think it's really hard to use. There's a lot of respect for it, but also a lot of fear. It's kind of like when I went surfing this weekend. I had a lot of respect for the ocean and a lot of fear. And it's a good thing because I'm alive. There is a language and library standard. We all know this, right? C++ 14 just ratified. But there's a lot of difference in that level of support across compilers and across apps and across platforms. So another challenge, especially even if you pick up C++, is depending on the compiler you're using, you might have different levels of support, meaning you're going to be writing a lot of if-defs. So that's another challenge. I think the bigger one for app development is that there's no standard around user interface. There's lots of user interface vendors. We're one. Qt, WX widgets. There's lots of choices, but there's no standard. And I think that's a problem for C++ adoption in terms of device development. The other problem is that, well, the platform vendors chose other languages and other solutions. Apple chose Objective-C for unknown reasons and resurrected a dead language. Now it's one of the most popular.
The reason is because they came from Next.
Well, yes. They bought it from Next, basically, yes. I mean, if you've done iOS programming, you see NS everywhere. You know what that NS stands for? Next step, exactly. And Google chose Java for their language. And I think the reasons largely were because they wanted to have control over the ecosystem. They wanted to be able to sandbox. But it's not really a language problem, although that was probably the reasons why they felt like it would make a better choice. I think on for Google, I mean, Java was popular in the back end especially, so you can find more developers to move them over that way. C++ was just as popular. I just read a report recently where it says C++ is still the most popular language. Well, of course, they lump C in as well. But between C and C++ as a combo is the largest used language still in the world. So there's a lot of C and C++ developers out there. Let me do a quick time check. OK. So I think that's probably the reason. These are the main reasons in my mind why C++ hasn't been widely adopted for device development. In the embedded space, it's everywhere. I mean, if you're writing a medical app or you're writing a network router app, or it's just a C++ world. There's no other choice. So it's interesting it hasn't made that transition to the mobile devices in particular. So what are C++ developers doing? Most are doing what's called a hybrid application. So this is managing as much C++ source code as you can that uses things like the RTL, CRTL, the STL, and interfacing with the native language of that platform. For the presentation layer, they tend to have choices here. One of the choices is they can use the APIs in the provided language by the vendor. So that would be Cocoa APIs with Objective-C and iOS, and that would be Java and Dalvik on Android. And there's challenges in doing that, but it's a way you can do it. Another choice that's been popular is to use web technologies on the front end, HTML5, JavaScript, you can write bindings. PhoneGap provides some compatibility between devices, access to sensors and those kinds of things as well. So this has been some of the strategies that C++ developers have had to take up until now. So if you look at a simple app architecture, everybody likes to talk about the simple tiers in terms of architecture. You have a presentation layer, you have some business or application logic, and you have typically some data access or backend. Now these can be all on the same device, these can be across many tiers, but this is the basic architecture. And if you're building this layer on each of these devices using the native languages, then you're basically doing a lot of coding. Even if you're trying to share C++ code across these, which you can do because there are C++ compilers, you still are spending a lot of time and effort writing individual APIs, having to manage basically separate code bases across them. Not just language and APIs, but also tool sets. So that's where you see this strategy come out of, which is let's try to maintain as much C++ source code as we can. Now for game developers, this actually isn't as big of a problem. How many of you out there write games for a living? So this isn't as much of a problem because you don't have to necessarily rely on native user interface controls. Generally, you're drawing to the GPU canvas through OpenGL, and you build your own controls. And so you have, is that largely how you guys do that? Yep. Unless you're writing a casual app, then you generally may want to try to use some native controls. But if you're writing to the GPU, you can draw anything you want. You can draw your own widgets. For those of us that are writing more businessy or consumer-oriented apps that aren't games, then you try to look at a way to deliver the native experience and manage or leverage as much C++ source code as you can. So that presentation layer then is different for each of these devices, where much of your source code then is going to be really low level or application logic for the most part. So in each of these, they have different APIs, they have different languages that are supported across them. For the most part, not to disparage Windows or BlackBerry, but most people are just worried about iOS and Android these days. Not to say that you don't have to deal with these for some customers or some target consumers, but it's mostly an iOS and Android world. And as we talked about, another option is to use web technologies like HTML5 and JavaScript, and then do bindings down to your C++ source code, which is generally straightforward for somebody who can do C++. Writing a language binding isn't that big of a deal. The other way around, if you're a web developer trying to language binding, trying to write one would be, I think, a bit of effort. So the way we look at the world is, because we have the access to C++ compilers, actually we write our own compiler as well, and UI controls can be presented to either call the native platform or draw themselves in the GPU, because all controls are, at the end of the day, are bitmaps. Then we're trying to take a holistic approach to C++, and that's part of what drives our solution, and also I think enables some of the rapid prototyping that we were talking about with C++ in particular. Now, the rapid prototyping solution, again, is not language specific, but in order to make C++ do it, some things need to be supported in the language and in the framework, and that's what we'll get into next. So this is what we see as the ideal approach. Just write one C++ code base, and you rebuild it for your target device. Saves you time and money. So let's get into rapid prototyping now. So we're trying to build applications that leverage as much C++ source code, or ideally all C++ source code, across multiple platforms. And at the same time, we're trying to deal with this new world where if we don't get this kind of feedback from our customer quickly, then we're going to waste time trying to fix user interface issues down the road. And so hopefully made the case that rapid prototyping is useful. Again, independent of any language or framework or anything you use, rapid prototyping is useful. Some languages are better than others. Languages that have sandboxes or virtual environments tend to be good at this because the app is running while you're developing it. How many saw the announcement from Apple a few months ago about Swift? Okay, so Swift is kind of, I guess, the death of Objective-C to some extent. But the big feature they talked about was the sandbox, or I forget what they called it, playground, sandbox, playground. It's a virtual environment. You're writing the app, you see the stuff happen live. That's really, really useful. I agree with them. This is an important feature for app development. That is, in a nutshell, rapid prototyping for yourself, for your customer. Now, where it becomes useful for the customer is when he's coming in regularly to give you feedback on it and to see it working at various stages so that you can deliver against his expectations or his or her expectations. So it kind of comes back to reducing the cycle between writing code and seeing it run on the device or on the platform. This kind of harkens back to, speaking of Borland, one of the things Borland did that I thought was really impressive at the time was they took what used to be very separate activities, which was editing code, compiling the code, and debugging it, and put it into one environment. The IDE was born. It was mostly the Turbo IDEs back then. How many of you used a Turbo IDE? So it was awesome, right? You could write your code in one editor, you can hit a button and compile it, you can set a breakpoint and debug it. And what that really did was it reduced this edit, compile, debug cycle. Before that, you would write your code, you would go to another terminal, you would type make or whatever build system you were using, then you would get your app up, and if you had to attach any debugger, then that was another terminal that you had to set up and manage. It was a lot of work. And that cycle took, maybe it was an extra 30 seconds every compile cycle. But depending on the size of your code base, smaller code bases, you may do this, several, maybe 100 times a day. If it's a larger code base, maybe a lot less. I mean, a lot of C++ developers tend to have very large code bases, so usually you're waiting for a build, and it comes every day. But if you're doing a local build and you're trying to test some changes, this is something that can get in the way. Those seconds add up throughout the day. Oh, thank you. There's my time check right there. Awesome. So he's reducing the cycle time between me looking at my watch. OK, anyways, so here's how we do rapid prototyping. One, we try to stay as local as long as possible. Sending a packaged app to a mobile device can take 30 seconds, can take a minute. God forbid you use the Android emulator. Has anybody used the emulator? Don't use it. Use a device. It's horribly slow, especially if you're writing C++ code, which doesn't make any sense. The device, right? The device can be slow as well. So yeah, try to stay as local as long as possible. Now that's not always easy when you're relying on services like, let's say, a GPS, or actually most laptops have that now. Let's try another one. How about an accelerometer? Oh, they have those too. Well, anyways, there's services that you can't always get on your laptop that are available on a device. So sometimes there's some things you can't do, but you could certainly paint your UI the same locally. Again, no reason why you can't do that to provide that feedback as local, stay local as long as possible. The other thing is you want to try to deliver that visual representation of the app during your development. If you're working, and this is a little thing, like showing the Chrome of a case of an iOS device and the case of an iPad tablet, not really necessary to do your development, but it helps you visualize what the app is going to finally look like towards the end. It's a little thing, but it makes a difference. So you try to get as close as you can to app reality during your design and development cycle. Almost every tool out there has some type of designer now. So that's how you're going to be largely interacting. But the more you can make that like your end product, the less time you have to spend in the cycle of building and deploying and testing. So you also want to try to present as much of the app as possible during the designer coding time. This is, again, more than just UI. This could be a SQL query on a database backend. This could be a REST call out to a cloud service. This could be some type of logic that you want to run. And this is where you see something like the playground that Swift brings as interesting, right? Because it can actually run the code while the app is being developed. That's really useful. C++ can do this too. There's lots of people experimenting with different ways to do this, and we have a way that we do this as well. But that's really the key. Being able to present as much of that app running live during your design and development time is going to give you much more of a rapid prototyping experience. And along those lines, if you can present real-time data, whether that's prototype data or a query that you make, it's actually going to fill out your UI with the result set. So you're going to see what the fonts will look like spaced correctly with actual data. You're going to see what the, let's say it's a list view or a table view, what the heading and each of the list view items are going to look like. It's hard to see that if you just have an empty control. So you want to populate that with some type of data that's going to draw text in the font that you're going to use on that end device so you can actually see what the layout's going to look like. So this is all in an effort, again, to reduce that cycle time and try to keep us on the local development environment as much as possible. C++ seems like it's going to be difficult to do that with because it's a compiled language, right? But if there's designer support tooling, if there is framework support, meaning you know how to instantiate objects at design time, if there's a way to host those objects inside your design time environment, then you can get to this. Oh, and lastly, a way to draw the UI controls correctly so that they look like your end product inside the design environment, then we're getting closer to this rapid development experience. And that's what we're trying to solve in this new world. So visual design and prototyping, you have to have visual design really to do rapid prototyping. Otherwise, you're going to get into that cycle where you have to deploy and distribute in order to get that feedback. That's valuable too, but this is a faster way to get that feedback. You could have a customer come in and sit there right there at your development environment with you and make changes live with them to meet their expectation. Much quicker cycle. Let me give you a quick example of what this looks like. So in order to do this, I am going to switch to higher resolution. Okay, then we're going to switch over here. Okay, so I'm just going to create a tabbed application here real quick. So this is like most development environments you see, whether they're in Java or Objective-C or C# or other script languages. Generally, most people have adopted the methodology of doing some type of visual layout inside your development environment and generating code to present that layout. That's basically what's going on here. These are user interface controls that are being represented in C++. And we can go to some source code here. So this is just basic standard C++. And there's your implementation file and the visual representation of it. So in order to make this work, you could write pure code. I mean, we talked about C programming using Petzold, right? You wrote pure code back then. It's really hard to write a designer that can read that code and present the UI, because you could write bugs real easily. How many of you write bugs? I'm just kidding. I think I probably spend 85% of my time debugging my code. In any case, it's really hard to just read pure code and present a user interface because lots of things can go wrong in the code. So the mechanism that works best for this type of approach is something where the UI is defined via text, whether that's structured XML or just plain text. We take a plain text approach. And the properties, or the things that are managed at design time, can be read from this file. Things, for example, like the width and height and location of a control. So you could write that in code, or you can also just manage it in a text file and stream it or read it at design time. We use a streaming approach. It basically means it's a memory stream that's keeping track of a text file. So here's the text file. Again, this could be structured XML, this could be plain text, it could be binary, it can be whatever you really want it to be. Text, I think all developers agree, is much friendlier to work with. Again, it's things that don't need to necessarily be dynamically generated in code. You can manage it statically at design time in one of these text files. Okay.
The first time I've seen a config file a long time ago wasn't XML.
Yeah.
JSON, but it was all XML.
Yeah, and XML is nice for structure, but it also takes longer to parse and process, and lots of memory. So, hey, plain text.
Props for you guys for not using XML.
But we used to use binary, and then we got in trouble. People said, give me text again. Oh, for future reference feedback and questions, we'll need the mic just to capture it. And we'll make time for questions at the end as well. Although I do like the back and forth, so I don't mind at all. Okay, so that's one aspect. Some part of the UI is best if it's handled not just in pure code, is managed by UI. How many of you used MFC or Object Windows Library, any of those? So those are pure code approaches, right? Notice there's not a lot of designers in the front of those things. And that's, again, because it's very difficult to just read pure code, especially when people can introduce bugs very easily and break things. So this is a safer way to manage it and keep a productive environment, while at the same time generating code where you need to really generate code for things like event handlers and those kinds of things where you're going to have to actually write code in them. So for an example, if I had a button in here and double click on it, then I have an event handler that I can do something in, right? Write some C++ code there. So that's the first aspect. Now, the other part that I talked about is let's stay as local as possible, as long as possible. So the other way you do that is by presenting what the user interface is going to look like for that proper operating system. So here, for example, is the iOS view of the same form. Notice a couple of things. The UI is drawn correctly for iOS 7. The tab control is correctly drawn at the bottom, contrasted with something like Android. So this is just a simple example where a control that does exactly the same thing is presented in the exact opposite location on both devices. So you either have to write separate user interfaces, you're going to have to deploy them both separately to get that feedback, or you can provide a designer that can give you that feedback right there in the environment. The other thing that really helps, I think, is presenting data live. So let's say we have a list of objects, and we want to display it in this first tab here. So if I'm just looking at a blank control, I'm going to have to rely on deploying this to the device and to see some actual data happening. Now, there's a couple different ways we can do this. One is we can inject prototype data, just made up information. The goal there is to have just some text that largely represents the type of text you're going to deal with. Maybe it's a customer database in a font that's going to be rendered like you're going to see on the device. So you see what the sizes look like, how much it's going to fit. These are all considerations in typical user interface design. So we provide what's called a prototype data. And you would just add some fields. So let's see, I'll pick bitmap names. And I'll do, I don't know, contact names. You can do colors and images and those kinds of things as well. But just to give you an idea. And then I'm going to connect these to my text. So we'll say this is item text here. So again, what this says is it gives you a visual representation of what your app is going to look like on that device so that you have a better sense of the spacing, the layout, and you actually have actual text to work with. This gives your customer also something to look at and say, oh, okay, now I see what it's going to look like. All we did was add text, but it makes a big difference in how you perceive the user experience and what's going to be presented to the end user. So probably the more ideal way to do this would be actually to go out and get some data and deliver it. So let me get rid of that. So popular today is, well, of course, you can make SQL queries back to a database. I'm not going to connect to a database right now. Or you can get data from a REST service. I mean, pretty much every web property out there that has useful data presents it through REST APIs now. It's really, really useful. One of the things that I've been interested in is the surf forecast, obviously. And when it's big, I want to know. So there's, I was looking around for APIs, and there is a few that provide REST APIs. One of those is called SppCast. So let me just add a REST client here real quick. We'll go to a web page also, a browser, I mean. Help. Stop it. That's frustrating. Okay. That's the joys of trying to work with Windows on a Mac. So this is a local California surf forecast, and they provide REST endpoints. So if you're building apps today, you're going to be dealing with REST. I mean, it's just everywhere. Cloud services, network, social networks, et cetera. It's all REST enabled. And so this gives you an example of the kinds of things that you can look up. Let me just look at the spot. So what's different about REST is it's asynchronous, it's stateless. So there's a little bit of management to use it, but it is a really simple format. Oh my God, that's horrible to read. But this is a JSON data packet. And this is basically the information that I just requested coming back. And it shows all the spots that I want to look at. So I'm just going to grab that real quick. So wouldn't it be useful to be able to see this live in the designer, right? This is the type of feedback that the customer is going to need. Again, I haven't left my developer workstation yet at all. And that's the really critical thing here. So we'll go to here and we'll say api.spitcast. Okay, that's my base URL. Then we'll make a REST request. Let's move these guys up here. Okay, and in the request, I'm going to give it that endpoint, that resource that I just looked up, which was API spot all. Now, this is a lot like the Playground environment, and this is something that is enabled because we've done extra work with the framework and with the language, actually, the C++ language, to enable this. But I can do something, for example, is execute that request live in the designer. So this is live objects that are living in the designer. Basically, what's going on behind the scenes is we've written a cross-platform framework. So what you see here is actually a Windows object that's hosted inside this IDE that's running on Windows, making that request. It's the exact same API that you would use when you deploy it to Android. In Android, we write to the NDK, and we wrap NDK up to provide that same API. On iOS, we do it with Objective-C. On Mac, same. But in Windows, which is where the development environment lives, this is actually Windows component in memory that's running inside the development environment. Question?
Your IDE is hosted only in Windows?
Yes, today. So let me get a response. Okay. And he should be connecting right back to the, I should see in here. Oh, I need to tell it here what my response is. All right, so now we have our response set up, and we should see the JSON in here, and we don't. Let me run that request again. How are we doing on time? 13 minutes, oh my God. I'm going to have to move on here pretty quickly. Now we see the content. Okay, so there's the JSON data packet now living inside the development environment. And so the next step would be just to basically connect it up to the user interface. So we use a little adapter here to turn that into an internal data format. And I need a data set. This is what actually talks to the user interface controls. So we just connect these things together. Okay, we make this active. Oops. So this framework basically, especially at this point, is a lot like connecting objects together. You don't have to write a lot of code to do these kinds of things. Of course, you can write code for all of this. These are all objects you can do dynamically as you write your application, but you don't have to, especially for a lot of these common types of things. So fields editor. So these are the fields that came out of the JSON. Okay, we'll add them all. And now we'll do that visual binding again. Again, stuff can be written in code, but we write tools that make it easier to do a lot of this stuff. And so what I'm going to take is the spot name. I'll take the county name, and I'll make that a header. And then I'll take the spot name, and I'll make that text. Okay. Okay, so now what we have here is a live request that's being presented inside the user interface. And this is really what's going to help an end user kind of visualize what's going on. The next step then is I could deploy this to my Android or iOS, no problem. But I'm going to run it in Windows because we happen to have written a Windows framework for this as well. And so I can actually show them, it's not going to be the exact UI, but it'll show them the data now running in Windows. They can see the live app. They can see the data running in there. And then when we want to deploy it to a device, then we select iOS or ARM, build it for that device, and deploy it. And that's when we get through that long cycle of packaging, deploying, distributing. iOS is painful to share applications with outside the App Store because you have to have provisioned devices, you have to have an Apple developer account, all this stuff needs to be set up. So my recommendation is if you're doing rapid prototyping is use Android. You can take those APK files, you can just put them on a website, somebody can download them. If they trust your content, oh, I was trying to build it for Android, my mistake. Sorry, what was the question? Oh yes, that's true. If you have certain types of accounts set up, you need certain enterprise level accounts to be able to share APKs more freely. That was test flight, yep. So Apple's trying to improve this, which they need to, because like I say, it's been painful up to this point. Android, though, by far is really easy. Oh.
But now to use iOS, you have to have an Apple Mac and a Windows machine. Right now, you need the Windows machine for the IDE.
No, I just run it in a VM, like VMware or Fusion.
OS, you run.
I run Parallels or Fusion.
Yeah, but you run Windows 7 on your Mac, but that's what you have to do.
Exactly.
You need a Mac to
Yep.
actually get that.
Correct. Okay, so I only have 10 minutes, so we're just going to pop into the final part of this. That was just an example of visual design and prototyping. Now, to make that happen, there's some extra support needed in the language and in the framework. It doesn't happen just by writing C++ code. One thing I mentioned, of course, is that these are Windows objects that are live in memory and hosted inside that development environment. And then when you build, you're binding to those libraries for that particular target. But the designer, you want to be able to provide the layout of the UI controls, allow people to modify design time properties. That's things like the location, the text, things that can be static that you can easily manage inside of a designer. Create event handlers. Of course, you have to do that when you do UI. And or display live or prototype data. So I hope you can see that's really useful when you're trying to get that kind of feedback. The way we do it is with the component-based framework. This is just like any kind of inheritance-based framework, but components have a little extra details to make them self-contained and hostable like you just saw inside that environment. Notice that when I did all that REST connections, these things were living independently of one another. They just created these links and were able to work with one another. So there's a rich hierarchy of components behind the scenes that are delivering a lot of functionality, and these endpoints end up using properties to make those connections, as opposed to using a pure inheritance-based model. So if you compare it to something like AL or MFC versus what we're doing here, they both are trying to encapsulate, in this case, Windows APIs, or Cocoa APIs, or Dalvik APIs. In the older model, where it was pure code generation in MFC or AL, for example, that was an inheritance model. Sometimes we went a little crazy with multiple inheritance, which we thought was a useful idea, but sometimes got us into trouble. Lots of challenges around managing vtables and leaving spaces for future methods to be added. I mean, it was really challenging to write frameworks, especially when you use things like multiple inheritance. Largely used fields, you had to write your own getters and setters, manage your own scope that way. It was all about pure code generation. And that didn't lend itself well to the design approach that we're talking about. So in this other approach, there is inheritance, but we tend to use the delegation model more so when sharing this data down the chain. One thing that's really critical here is the support for method pointers or closures, because that's basically how event handlers are built. Properties, these are ways to take public information or public fields and make them visible to the designer. And then I talked about these text file forms and streaming system, being able to manage the UI largely through text or XML. But one thing that's really critical here is we use a lot of RTTI. And C++ doesn't have a lot of rich RTTI support in the standard. Yes, you can cast objects, you can get some basic information, but we really need a lot more than that. So that's additional stuff that we've added to the language. So the things we've added to the language to make all this work is what we call PME. These are some extensions that enable things like properties, making public information available to the designer, for example. It sets up things like getters and setters, for example. We've added automatic reference counting for the framework objects themselves. You can still do memory management any way you want in your code. When you work with the framework, it's automatically reference counted for you to make it a little easier to work with. Interfaces, attributes, of course, generics and collections, STL is fully supported there. Now we finally have lambdas since C++ 11, but we had to write our own closures back then because those weren't available at the time. It's using, I wouldn't say it's a custom toolchain. We use Clang and LLVM. Yeah, but we've added features to the front end. Yeah, and we'll take that question in just a minute on here because I want to make sure I get that gets answered. So this is a look at the extensions. There's 5 of them that make all this happen. These are what we've added to Clang to make all this work. So I won't get into, this is basically us showing that we do use Clang, has a bunch of compatibility with Clang, and this whole cycle over here of design and development is what we just shared with you today. When you go to build, runs through the Clang front end and then uses LLVM to generate the x86 or ARM v7 binary for us. And in iOS, we build standard IPAs or .apps and IPAs. We bridge directly to Objective-C. In Android, we try to avoid Dalvik as much as possible. So we use the native developer kit, which means you write a little shared object. There's a little tiny Java stub that calls our shared object, and then we take over, and life is grand. Occasionally, we have to make JNI calls into Dalvik. Sometimes not all the services are available, but for the most part, everything's available in the NDK. So if you haven't checked out the NDK as a C++ developer, you definitely should. Quick review of objections we've heard. C++ is too complicated. This is my objections that I've heard. There's too many differences between platform support and no common user interface. And so, again, this is where we're trying to solve the problems. I think C++ 11 did a great job of simplifying the language. As C++ ambassadors, for those of us who know people who use Java or C# and are afraid to use C++, we can help them understand it's very accessible, again, and they should use it. But the combination of visual design prototyping, things like ARC, I think is all going to make C++ easier to use across these devices. In terms of the differences between platforms, we happen to use a common toolchain, Clang LLVM, which is a wonderful, in fact, I'm doing a talk Thursday morning or Thursday afternoon on a case study on us moving this to Windows. So that's, if you're interested in what we did there, it was a lot of work, but it was well worth it. Clang LLVM is awesome. Use a common STL, provide the same development environment and a common API. And then in terms of user interface framework, we provide hundreds of controls. These are a combination of what we call styled controls, where we draw the bitmap in the GPU, a lot like game developers would, or we can ask the operating system to draw a control on our behalf, depending on the control. And then all the other things that you saw today in terms of layout and stuff. So I have 3 minutes. Actually, we could probably go a little longer, right? Go ahead and ask your question on the mic if you would. And I will be open to questions over the next 3 to 13 minutes.
Yeah, could you talk a little bit more about how you modified Clang?
Sure.
Maybe bring up the keywords. And I noticed you mentioned automated reference counting, which is
Yeah.
obviously a technology that you use on Objective-C.
That's right.
So I'm very interested in how that compares to the Objective-C approach. And also you mentioned you're actually using the Cocoa libraries.
Yes.
So I'm interested in how you're doing that, because on the Android side, you're going to the NDK, so you're
Yep.
pretty much building everything from scratch. But how you integrate with the Apple side is a little more
Sure.
interesting.
So there's several questions in there.
Yeah, I'm sorry.
That's fine. So the first thing is with regard to Clang LLVM. So these are the extensions we've added to Clang and LLVM, or to Clang in particular.
Yeah.
These support this design time environment that you saw. The properties are what we use to take public members and make them available to the designer. All they are is public members, basically,
Right.
with getters and setters built in. Published means that it can be displayed in the designer. The closure is how we implemented callbacks. So this is a lot like Lambda operators now, but those didn't exist when we built this. So we're looking at possibly moving to that, but for now we have our own extension, which basically captures local variables and then can make the callback call for us. Class ID and Delphi RTTI, these are what we use for RTTI. And this is where we generate a bunch of information about the object. We use it all over the place. When you saw me doing that visual binding of information, those are RTTI calls. They query the object dynamically for that information to be able to display it inside the designer.
So this is from your Borland product, Delphi.
Yep, exactly. We built it out for multiple operating systems now, exactly. So the other question was with regard to Objective-C.
Yeah.
So there's a thing called an Objective-C bridge.
Okay.
Actually, Objective-C is pretty compatible with C, not so much with C++. So a lot of those calls, we make our C calls and we wrap them up into
They have an Objective-C++ sort of mode.
They do. C++ is actually, they use the Clang front end, first of all. So that's good.
Yeah.
So all the C++ is there, they just don't expose it well through Cocoa.
Okay.
So we had to wrap those objects in C++ to make them available. In the NDK, like you say, we build a lot of it from scratch. Yeah. But the NDK actually has a lot of features supported in it. I'd say 75% of Android is available in the NDK now. For the rest of it, we make a JNI call where we need to pull that information. And those are pretty cheap if you're not sitting in a loop. If you're sitting in a loop, they're expensive. If you're just making calls out now and then and you're storing that information, JNI's not that hard to work with. It's pretty quick. Last question was with regard to?
Yeah, the ARC.
ARC.
I was very interested about ARC and how that raises shared pointers in C++ and also ARC in Objective-C.
Yeah, so those models are compatible, although you don't want to necessarily, so this is how we look at the world. If you're using C++, use and resource acquisition is initialization approach, shared pointers, unique pointers, all those are use that in your pure C++ code. If you're working with the framework, let ARC do its job. So we just ARC enabled the framework. We didn't ARC enable everything. Right. And so Apple, again, gave us hooks in LLVM to make these calls. It was really easy to add ARC.
So you actually borrowed some of the Apple work on ARC that they did for Objective-C?
Exactly right. We make the same calls, actually.
Right. Oh, very cool.
Now, the question, is this a forked version?
Yeah.
We do, we intend and we do contribute back to Clang and LLVM, LLDB, all the ancillary tools as well. Not all of it's there. Mm-hmm. So these are commercial compilers that we build that are supported across all these operating systems. And I'll talk about it more on Thursday. Mm-hmm. That's one of the challenges of working with such an active open source project, is keeping up with it and making sure your changes get in there. But that's something we absolutely try to keep up with.
Okay, great. Thank you.
Thank you.
Earlier on in your presentation, you mentioned that one of the challenges is not only the different platforms, but also some of the different form factors, the smartphones, tablets. Am I right in thinking that you might want to define different views for each form factor? And what kind of considerations come into play when you're doing that?
That's an excellent question, and I didn't get a chance to show that. But yes, there's really a couple of choices. For each different form factor, you either have to write a completely different user interface, which means you can't leverage a lot of user interface code like event handlers, or you have to write something that dynamically lays itself out, which doesn't necessarily deliver the best experience. Our approach is what we call multi-device design, is that you saw the text form that we displayed. You do most of your work inside a common UI layout, and things like most of your UI controls and event handlers are shared. Then when you switch to another form factor, you create your deltas. You create your differences that you want to display in the form. So let's say you're going from a 4-inch device to a tablet. You have more real estate to work with along the width. So you would add more controls. And the object is still managed in a single form file, but when it streams in, when it instantiates that object, it streams in the shared code, and then it asks what operating system am I on, what form factor, and depending if you have an additional view created for that, it streams in those additional differences to present that form. We just invented this recently, actually, in our most recent edition. So we think it's a pretty elegant approach. It's a really hard problem to solve, though. So we think we got it largely handled, and I didn't have time to share that with you guys today, but that is something that absolutely is, I think, one of the bigger challenges. So 3 choices now: write separate UIs, write dynamic layout, or you can look at the way we did it, which was what we call a master detail or master view approach. Another example would be like when master detail in the phone, your view or the detail is mostly what you look at, and the master gets scrolled out generally with a menu or some type of drawer. On a tablet, it's always docked, or at least that's the typical UI conventions. So we built a API called Behavior Services, which the framework uses, developers can use to say, what operating system am I on? What form factor? How many pixels do I get to work with? What's my resolution? What's my aspect ratio? All the kinds of things that you would need to make layout decisions about are presented in this API. So that's our approach. I'm sure there's other elegant solutions out there, but it's no doubt a hard problem to solve, and we took a whack at it here in this most recent version too.
Thank you.
You're welcome. Any other questions? Go, please. Go ahead.
What apps out there are using this? Like if I wanted to see it shown off, like what the actual UIs look
Oh,
like, or
sure.
the things I could get?
If you go to our site, we do have a showcase. So there's quite a few that we have actually a large number of enterprise customers as well that don't publish apps through an app store, plus several that are getting into the app store now as well. So I'd say just visit the website and get the information.
How would you handle internationalization for an application here?
That's a great question too. That comes again down to internationalization is one thing where you're localizing from one language to another. That has a big impact on layout, especially something like, let's just use German as an example. One simple word turns into like half the length of the screen. So that's where it's going to be really useful to be able to see this in a prototyping approach this way. You basically, standard localization techniques, you keep your strings in a string table and have localized versions of those. So there's nothing fancy with regard to the localization aspect. You still need a human to actually generally do the localization. Same goes for like kanji or those types of Asian characters as well. Right to left actually is a harder one to solve with a lot of that script. But it comes down to string tables and font support, and being able to see your layouts generated, I think locally, is just going to save you pain when you have to try to deploy this thing, to even see what it looks like in the first place. I don't know if that fully answered your question, but.
What do you have different? You've got your text file, which is like your resource file or whatever.
Mm-hmm.
Do you have a separate one of those for each language?
Yeah.
So
Exactly. Yeah.
Sorry, just one more question. I mean, with anything cross-platform, in my experience, testing is a major burden.
Yes.
Do you have any tools to assist with that?
Yeah. Well, you get your standard source code debugger. You have, hopefully you're writing good unit tests, so there's unit test frameworks and those kinds of things as well. For UI, especially when you're writing to a GPU, that's a little more challenging to get that kind of UI feedback. So we're still working out solutions on that one. Other than the data elements, because you can query the RTTI to get what's in the object, but pixel by pixel kind of thing.
Yeah,
that's
I'm
what we're
thinking
still trying to work
Android
out.
is like, okay, it's got 85% of the market, but it's got like so much fragmentation in that 85%.
It's true, especially with the form factors, yep. So yeah, that's something that we're still trying to fully resolve and haven't fully figured out how to, game developers to some extent have it figured out because they write to the GPU all the time, but they're also not necessarily doing a lot of UI management like a business app.
Yeah.
There's more 3D engine code or 2D code, and a lot of times if it looks correct, it is. So I guess it's true of any app, really, but yeah, that's something we haven't fully figured out yet.
Yeah.
Any other questions or comments? Okay, well, I guess we got Bjarne's talk here in about 20 minutes, so I'm sure nobody wants to miss that one. Thanks, everyone.